Welcome once again to Blue Pen Land. This problem and a lot of the ones we're doing in this test are, these are like the database questions that begin paper 3. So everybody does, I think it's the first 2 questions, and then you go and find your options and do those questions. So these are supposed to be, experiments we might do in physics. So the student measured the height of the air column and the corresponding pressure. After each reduction in the volume, the student, so they reduced the volume by letting air come in here, right? The student waited for some time before measuring the pressure. Outline why this was necessary. Think about the temperature, right? If we reduce the volume, that's a compression of the gas. Something happens when you do an adiabatic compression, and they're trying to observe this at a constant temperature, right? Is it possible that maybe the temperature might change and then we got to let it stabilize? Anyway, just a thought. All right, and then on this part here, they say that if you graph the pressure versus 1 over the height, right, they get this thing here. So as the pressure increases, of course, the height is really going down, but 1 over the height goes up, which is kind of fun, right? But what they're doing is they're linearizing this graph. So the equation of the best fit line is P equals A plus B. And basically it's in the form of Y equals mx plus B, only this is like what it is for B, and then B is like the M, right? And then 1 over H is like the X. Just think of it that way. So find the value of B, which is going to be the slope of that line, right? What I did was I just used this point right there and that point right there and just did rise over run. And when I did that, I got right in the middle of the range. If you look at the mark scheme, they give you the range, right? And then what is the appropriate unit? Well, the slope of this is going to be pascals divided by the whatever this is, right? The rise is going to be in pascals. The run will be in meters to the minus 1. So pascals divided by meters to the minus 1. Figure out what that is. Okay, that's the appropriate union. And that's one of the marks, okay? And then it says, outline how the results of this experiment are consistent with the ideal gas law at a constant temperature. Well, the height of this thing, right, this height here, this is proportional to the volume, right? Okay, and so the ideal gas law, we would say if it's a constant pressure, we would say that PV equals PV, right? And so as the pressure increases, the volume actually decreases. And so in this case, the height is standing in as a proxy for the volume, right? It's directly proportional to the volume. So talk about that. And then I missed a mark. There's a mark that you have to say, okay, you should get this data, and then if you look at this graph, you will get this data. So make an argument about the pressure and the volume, okay? And then say, you have to also say, and I missed this mark, you have to say that this graph, it looks like that, right? Okay, and then this guy says the cross-sectional area is 1.3 times 10 to the minus, what does that say? I can't read it on this screen. 10 to the minus 3rd square meters, which is quite large. I think I figured out that it's like 3.5 centimeters in diameter, right? Okay, so that's the cross-sectional area. The temperature of the air is 300 kelvins. Estimate the number of moles of air in the tube. And you're like, well, how can I do that? And then do they give us a graph? They do. So I think what you can do is this. We need, basically the number of moles is going to be PV over NT, right? No, PV over RT. Is that right? PV equals nRT. Yes, okay. So I would measure, this is our pressure right here, right? Is 1 times 10 to the 5th. So now we've got a pressure. The volume is going to be, well, we got to figure out the volume. The height of the tube isn't, if 1 over the height is 2, then doesn't that make the height of the tube 50 centimeters? I can't remember what I used. Did I use that? I did, yeah. 50 centimeters, half a meter, right? Okay, so the volume of this thing is the area of the times the height, right? So it's a right circular cylinder, right? The height of this is the area of the top, and they tell us that the area is 1.3 times 10 to the minus third square meters, right? And then the height is 50 centimeters, so 0.50 meters. So what you're going to put in there is this times this. That's your volume. R is that, and then the temperature they tell you is 300 kelvins, right? And you can find the moles. And then, finally, the last one here, in the equation, B may be used to predict the pressure of the air at extremely large values of 1 over H. Suggest why this will be an unreliable estimate of the pressure. Well, at extremely large values of 1 over H, the volume is very small, right? Because if we have 1 over a micron, right, 10 to the minus sixth, that would be a million, right? 1 times 10 to the sixth, right? So at exceedingly small values of volume, right? Remember, the ideal gas law breaks down because one of the assumptions of the ideal gas law is that the molecules don't take up any space. But of course they do, and so at small volumes, the space that the molecules actually take up, affects the accuracy of the ideal gas law. Okay, so basically, I think what you need to say is that that's going to be a very small volume, and the other thing that happens too is that the molecules, when they get close enough together, actually attract a little bit. So you get, as you approach that point of like maximum compression, I think the pressure is less than what you might think, and then it's more than what you might think, or something like that. But anyway, yeah, the ideal gas law doesn't work when the molecules are close together. Okay, so just keep that in mind. All right, I think I've talked quite enough about this one.